So the football is kicked and it leaves the ground at an angle of 40 degrees above the level, above the horizontal. And the ball returns to the ground after 3.3 seconds of flight. We want to figure out its horizontal displacement while it's in flight, in other words, its range. And we would also like to figure out the height that it reaches above ground, the maximum height. So pause the video, attempt the solution, and when you're ready, push play, and we'll solve it together. Okay, so the first thing that I recognize is that it starts on the ground and it ends on the ground, which means that I initially would try to, since the question was, what's its horizontal displacement? That's its range. And you would like to say v squared sine 2 theta over g. But you can't do that here because we don't know that initial velocity vector. We only know that it's in the air for 3 seconds and that it left the ground at 40 degrees. So let's set up an XY coordinate system and see what we can determine from that. Our X and Y motion, V naught V A T X, V naught V A T and Y. And let's follow our problem solving strategy. Let's fill in what givens we can determine. We don't know, I'm starting with the Y, we don't know its initial velocity. We don't know the final velocity. What do we know? Well, those two, if we're talking about the entire 3.3 seconds of flight, they will have the same magnitude, but the final velocity will be coming down, so it will be a negative. And the acceleration will be gravitational, downwards, negative 9.8 meters per second squared. We know that it is in the air for 3.3 seconds. We know that it begins and ends on the ground, so its y displacement is 0 meters. So from this, if we take a brief look at the x side, we already know that v naught and v will be the same because the ball will not accelerate in the x dimension. So we really don't have a lot to work with on that side. So coming back over to the y dimension, we do have enough information to find that we could get v naught with the quadratic. So if we say y is v naught t plus a half acceleration time squared, I believe we know everything in this equation but v naught. So let's see if we can solve for v naught here. Y minus a half at squared is v naught t. And dividing by the t, we would have y, minus 1/2 at squared over t. We could cancel a t here. I think that this will give us our v naught. So substituting my values into this, the y is a 0 minus a half. Acceleration is negative 9.8 and the time is 3.3. And if we put this in our calculators, it looks like an initial velocity of about 16.17 meters per second. So we know that the initial y velocity was 16.17 meters per second. We can get that final y velocity now if we need it. I'm not sure yet that we do. I think that if we look at the initial velocity as being the hypotenuse of a right triangle, where the components are the initial velocity in the y direction and the initial velocity in the x direction. The initial y velocity is known now. That's 16.17. And so I think that I can determine what this initial x velocity is, because the tangent of any angle is the opposite over the adjacent. So if I want to solve for v naught in the x direction, that is adjacent to this angle. So the adjacent is the opposite side over the tangent of the angle, and our opposite side is 16.17 over the tangent 40 degrees, gets me an adjacent side of 19, call it 19.27. So our x velocity is 19.27 meters per second. So now that we know this, I think we can get x, which is the range that was asked for in part A. Because if the acceleration is 0, then x is v average t, 19.27 for 3.3 seconds. It's about 63.6 meters. There's the range. So we know 63.6 meters is the x displacement, the horizontal displacement. And now the next part is, what is the maximum height reached above the ground? Well, that's not the 3.3 seconds, because if you think about the trajectory of the ball, it leaves the ground and it returns to the ground, and the entire trip through the air took 3.3 seconds. If we're looking for max height, that's halfway through the entire trip. And if all we're looking for is the maximum y displacement, who cares about the x direction? All we need is the y. So we already know the initial velocity in the y direction. It's 16.17. So why don't we say, to find a maximum height, let's just theoretically think about an object that is thrown straight upwards into the air, vertically upwards at 16.17 meters per second. How high will it go? In that case, we would set this up to say that v naught is the 16.17 meters per second. The final velocity, well, at maximum height, its y velocity is 0. The acceleration is gravitational, downwards at 9.8. The time, yes, we know it's half of that 3.3, but we really don't even need that, because y is what we're looking for, and with v squared is v naught squared plus 2ay, we can solve for y. Zero minus whatever 16.17 squared is, to negative 9.8. This looks like about 13.3 or so meters. That is the maximum height reached. 13.3 3 meters. Okay. I'll try to show the entire solution here. So there we go. There's the entire solution. I hope it's not too small. So let's take a look at one more briefly. And this time a projectile is launched from the top of a building. And this building is apparently 40 meters tall. So the initial velocity is 20 meters per second, angled upwards, so 40 degrees above the horizontal, from atop this 40-meter tall building. And let's solve for the total time that it's in flight. That's part A, time in flight. Part B, X. Let's let that be the projectile's horizontal displacement. In other words, how far from the building will it land on the ground? Part C is the velocity at impact. In other words, what is the velocity of the projectile the instant before it crashes into the earth? Part D, what is the velocity of the projectile 1.5 seconds after it has been launched? And part E, we want the acceleration when the projectile is at maximum height. So pause the video, work the solutions. When you're ready, push play. Okay. The projectile is obviously going to move in 2 dimensions. So X and Y. And what do we know about its motion? V naught V A T X, V naught V A T and Y. We can get its initial X and Y velocities because the initial X velocity is this horizontal component, V naught in the X direction, and this vertical component is the initial Y velocity. So it looks like V naught Y is 20 sine of 40 degrees. And that's about 12.9 meters per second. And the initial X velocity, that is an adjacent function, 20 cosine of 40. And that will give me an initial X velocity of about 15.3. And once the projectile is in the air, the velocity will not change. So V naught and V are the same because the acceleration is 0. So we can treat V naught and V as just V average now in the X dimension of 15.3. We don't know the time, that's what we're solving for. And time is a scalar. It doesn't matter which side you solve for it on. But there's not enough information on the X dimension. So back on the Y dimension, I don't know the final velocity, but I bet it will be coming down. I'm going to put that negative there. Gravitational acceleration is downward at 9.8. T, I think I'm looking for that. And Y, well, it will start at the top of the building, and it will move in the negative Y direction until it impacts the ground. So the displacement of the projectile, regardless of the path it follows, remember that would be distance, displacement is negative 40 meters. I think I can use the quadratic and solve for time, or since in part C I have to know the velocity anyhow, let's go ahead and find that final Y velocity. So V squared is V naught squared plus 2AY. So when I want V, I have to take the radical. And please remember, this will not work out to be negative, which was why we put the negative over here on the velocity to begin with. So this looks like run this through your calculator. It looks like 30.8 or so meters per second. So we know that it's coming down 30.8 meters per second when it reaches the ground. So now we can get T straightforward. T is V minus V naught over A. Remember, that's just from V is V naught plus AT. Rearrange to solve for T here. The final velocity is a negative 30.8. The initial velocity is 12.9. And let's divide that by our acceleration of negative 9.8. This looks like a time of 4.6 seconds. That answers part A. So the time in flight is 4.6 seconds. So now I think we can get our range easily enough. It looks like X is V average T, 15.3 for a time of 4.6 seconds. And that's 70.4 meters. So there is our horizontal displacement. Now this velocity at impact, well, it's coming down at 30.8 meters per second here. The final Y velocity, and it's still moving to the right at the 15.3 meters per second. So this is the vector we're looking for, the resultant here. Put these two components together. This hypotenuse is the velocity that we are looking for. And let's not forget, we need a direction. So if I solve for this angle, then that will be the same as this angle, and I can state this downward velocity as being so many degrees below the horizontal. Pythagorean's theorem, it looks like this velocity is 30.8 squared plus 15.3 squared. That's about 34.4 meters per second. Now let's get this direction, an angle. And if I'm solving for this angle, I know all three sides at this point, but this 30.8 and 15.3 are readily apparent. So opposite and adjacent, that's a tangent function. To find the angle, the inverse tangent of the opposite side, 30.8, over the adjacent side, 15.3. And looks like our angle is about 63.6 degrees. So that velocity then is 34.4 meters per second. At 63.6 degrees below horizontal. Right, so magnitude and direction. There's the velocity vector at impact. Okay, so now for the velocity at 1.5 seconds, that is a different problem because everything that we've solved for already is for the entire 4.6 seconds that the projectile is in the air. And now all of a sudden we're being asked to evaluate the motion 1.5 seconds from the beginning. So we're going to have to do this one a little bit separately, but it's not that big an issue because the only thing that's going to change is the y velocity. The x velocity was constant, 15.3 meters per second, the entire time it was in flight. So we're basically looking for a velocity vector v where we already know the adjacent, this x component is 15.3. So if we knew the vertical component, we could just play with this right triangle to answer part D. So I think we can get that velocity. We know that initially in the y direction the velocity was 12.9. So now let's simply change our time to 1.5 seconds and find that velocity at 1.5 seconds. So in the y dimension only, the initial velocity was 12.9 meters per second. V is what we need for this vertical component. The acceleration is downward at 9.8 meters per second squared. The time is 1.5 seconds after being launched. We don't need the y displacement. Let's get this velocity. So V is V naught plus AT, 12.9 plus the negative 9.8 and the time of 1.5 seconds gives me a velocity of 1.8 meters per second. So now we know this is 1.8 meters per second. I think I can use Pythagorean's theorem to find this hypotenuse. Yeah, and that's about 15.4 meters per second. So there's the magnitude of the velocity, 1.5 seconds after launch, 15.4 meters per second. But this is velocity, so let's find an angle. And I think that I can simply do an inverse tangent function for opposite of 1.8 and adjacent of 15.3. So tangent minus 1 of opposite over the adjacent. And it looks like, okay, it's only 6.7 degrees above horizontal now. Okay, that answers A, B, C, and D. Now, the very last part, what's the acceleration at maximum height? We don't need to solve this. It's a projectile. It moves under the influence of gravity. So this is G, which is downwards at 9.8 meters per second squared. Now, the velocity at maximum height is 0. But that doesn't mean that that isn't changing, which is what acceleration is. So if the velocity is changing from a positive upward direction to a negative downward direction, and we evaluate that motion at every instant of time, then at some point on its way upwards, its velocity will decrease to 0, but it is still in the act of changing in the downwards direction, and then it begins to increase in the downwards direction. But at that instant, whether it's moving or not, its acceleration is downwards at 9.8.